Good morning, quantum enthusiasts. Today is going to be a great day. It's like, well, we're going to almost finish factoring. I probably will leave one loose end untied up and also a little bit of number theory tied up. But we're going to really hit it hard today and more or less see the end of the quantum factoring algorithm. So let me remind you where we were last time. We kind of saw the whole overview, the gist of it, and there was one crucial technical part that we had to still work on, and that's what we're going to work on today. So this is the summary. We're trying to factor some enormous 1,000-digit, 2,000-digit number, capital N, product of two primes. And we had this funny way of doing it that involved considering all the powers of 2 modulo n. And we made classical code, and then we could also turn it into quantum code that just multiplied a number by 2 mod n again and again and again. And we saw that would eventually loop back on itself and get you back to 1. And if you let S be the set of all powers of 2 mod n, then we drew them on in this circle, and we saw that doing times 2 mod n just kind of wrapped you around this circle. And we wrote L for the number of elements in this circle in the set S. And we saw that if you could just figure out what L was, some other thousands digit number, then you would do 2 to the power of L over 2, and then GCD of that plus or minus 1 with n, and you would factor n. So we were like, OK, all we have to do is figure out capital L. OK, and let's say this is a quantum operation now, so it's got some unitary associated to it. And in this lecture, we're going to be thinking about this geometrically rather than as, it's kind of the same thing as this quantum code, but rather than thinking of it as quantum code operating on qubits, we're going to think of it geometrically. And really, actually, I kind of wrote it over here in an example where n is 21 and this set L was 6. These were the powers of 2 mod n. And it's not important. It's 1, 2, 4, 8, 16, 11, but it doesn't really matter what they are, as we'll see. It just matters that there's 6 of them. And if you apply R to this first one, you get to here. And if you apply R to this, you get to here. And if you apply R to here, you get here, 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 and back here. So geometrically, there's some 6 basic states out there in space. And if you apply R successfully, it cyclically shifts among them. And we said the main plan would be to do rotation estimation on this unitary R. Now, rotation estimation needs a starting state, and ideally one that's in one of the planes of rotation for R. But we don't know anything about the planes of rotation for R yet. That's pretty much exactly what we're going to study in this lecture. But the algorithm will not be able to pick one. So it's just going to use the first basic vector, corresponding to the number 1, because at least it knows how to make that. And the key claim is that if you do this, rotation estimation on R with this starting vector, then you get out something interesting. You get out a random number. It's a random angle. And it turns out that it's a random fraction of tau. Tau is 360 degrees, a whole turn. It's a random fraction of a whole circle with L in the denominator. So it's either 0 over L, 1 over L, 2 over L, 3 over L, up to L minus 1 over L. And we called this a clue for what L is. And we at least illustrated last time that if you just do this whole procedure again, basically make qubits in the state, do rotation estimation, then you'll get some random clues with different k's in the numerator. And we saw that if you got a few such different k's, there was some classical algorithm that would let you figure out L and thereby factor n. So that was the plan. And I circled this bullet point of the plan because this is all we have to do today to understand this. OK, so I even mentioned last time, if you look at it in this way, it's kind of similar to some little examples we studied before. These little examples where we looked at the operator that increments a number mod something 3 or 4 or 5. We saw increment mod 3 in class. We sort of illustrated it to illustrate this 2D planes of rotation stuff. And you studied mod 4 and mod 5 on homework. And now it's basically the same thing as increment mod L. It's just these basic states, instead of being called 0, 1, 2, 3, 4, 5, they have these different names. But geometrically, it doesn't really matter. These are just some L perpendicular states. So what we really need to understand is what are the planes of rotation in space for this kind of increment operator or cyclic shift kind of operator. And that's what we'll work on. It's a very geometric problem, and it's funny, and it'll take some math work, and it'll be a little bit like complicated. But that's our challenge for the day. And you might even like find this very believable in the sense that, you know, we know that if you do this R many times in a row, you'll get back to where you started after L steps. So these rotation angles for the planes that R rotates, like they also have to have the property that like if you do the rotation like L times, you have to get back to where you started. So they should be like, in fact, they kind of have to be like integer over L fractions of the circle. And kind of what we're going to show is that like, in fact, like each integer fraction over L of the circle occurs. And you know, this is some kind of like, it's not in any one particular of them, but it's like equally, it's like an equal mixture of all the different, of being in all the different planes of rotation, and that's why you get each of the possible fractions equally likely. Okay, so the first thing we want to do is like simplify our lives a bit and pretend for this study of capital R that we're in L-dimensional space. Now, actually, we're not in L-dimensional space because, you know, if we're in this example, for example, we're like encoding numbers with 5 bits. So there's actually 32 possible basic states. So really, R is acting in 32 dimensions. But we're going to only be like sort of starting with this basic state. And like rotation estimation just applies R a bunch of times in various different ways in superpositions. So actually, the algorithm will never construct a state that has amplitude on anything other than these 6. It'll always stay within this, you know, 6-dimensional subspace. So what I'm saying is like every state that this whole algorithm ever constructs will look like this. It'll have some amplitude on this first thing, second, third, fourth, fifth, sixth, or elf. So we can kind of think of it like a generic state as looking like this, where u through z are the amplitudes. Now, what I want you to think about now is like, what if you were to apply R to this state, like a completely sort of general state? What do we get to? Well, R changes this 1 to this 1. So we'll get like u times this basic state. And even though I calculated it first, let me write it sort of down here. So I'll get 0, 0, 0, 1, 0 times, got to do all these colors, u. OK. And yeah, let's see. R applied to this piece of the state is like v times R applied to this. R applied to this is this one. So we get v times this, 0, 0, 1, 0, 0. That was colored red. And if you continue on this way, I think you'll agree. Let's see. That we'll get w. Let me just do all my colors here, and then I'll talk it through. I think you probably see where this is going. Yeah, what we're going to get to is this state. Okay, so applying R to a completely general state with these amplitudes gives you another completely general state. Well, with like the same amplitudes, but just like cyclically shifted down by 1. Okay, so what we're going to start to do now is write our most general states just as like height L, or in this case height 6, column vectors, at least temporarily. So I won't do the colors, but we're just going to write it like this. R sort of acts by like cyclically shifting this down. And basically, what I'm trying to get across is that we can now just pretend everything is happening in 6 dimensions, or L dimensions. And we just write our states like this. And now R really looks like this, I don't know, increment mod 6 operator, just the operator that like, cyclically shifts down by 1. Okay, and this will help us like understand, well, it'll make it easier for us to focus on the question we're after, which is like, what are the 2-dimensional planes of rotation for this unitary operator? So this cyclic shift by, of length 6 operator, there are some 2D planes in which it's like doing different rotations. We want to figure this out. So for this crucial claim that we're working on here, we would need to understand like this operator's planes of rotation. And I suppose also, by the way, we should point out that like start in this picture is this one, just 1, 0, 0, 0, 0, 0. Yeah. Okay, because it has all its amplitude on this basic state. Okay, any questions? Okay, so now it's like a kind of like a geometry, math, linear algebra problem. Really, I mean, if you like to hear different math terms, this R is like the adjacency matrix of a directed cycle of length 6. And it's kind of what we're doing is like we're kind of like finding the eigenvalues of that matrix. But we're going to think of it as like these 2-dimensional planes of rotation. OK. So you might have remembered doing this very problem when L equals 5 on the homework. And I mentioned there, the way we did it was like kind of annoying. There's like this like golden ratios, and there's like a lot of calculations, and it wasn't like very obvious how to do it. But it turns out there is a trick, as I mentioned in that homework problem. There's a trick you can do that makes the math a lot more pleasant. And it also has like a nice connection with quantum and the EPR entangled state that we talked about before. So we're going to do this trick. Now, this trick looks a little unmotivated or like weird. But just accept that, because it's like the trick that will make our calculations easier. OK, so a trick that makes this task nicer. One weird trick. OK, so really, let's go back to the code point of view. This R is really coming from this times 2 mod n operator, which operates on like 5 qubits, or in general, I don't know, thousands of qubits. So let's give those names. So like this times 2 mod n that we're studying operates on some qubits, A1 through A little n. And we're imagining doing rotation estimation on qubits, n qubits. So this is the trick. We're just going to introduce, and the algorithm can really do this. It'll like introduce one new qubit, which we'll call B, as we do. And now we're just going to think of this code times 2 mod n as operating on these n plus 1 qubits, A1 through n, together with B. And it just doesn't do anything to B. That's like really weird. Like it just it ignores B. It does what it always does on A1 through AN. But nevertheless, we're going to think of this as an operation on A1 through AN together with B. OK. So I'm going to sort of retroactively redefine what R is. I'll say R is the unitary for this. So let R be the associated unitary on A1 through A n and B. So in our example, now sort of the starting state will be, will end up being, let's say, well, never mind the starting state. Now, a state might be like, OK, this encoding of 1 in the A bits, and some other vector qubit state for B. And R, how does it act on this? Well, it just ignores this qubit and just does what it always does here. So we get 0, 0, 0, 1, 0, tensor V. OK, so this could have been 0, ket 0, could have been ket 1, it could have been something else. But the point is, R just does what it always does on A1 through AN and ignores B. OK, so similarly, if we got to this state, and this was some other vector, again, we just cyclically shift the first 5 bits. Well, we do R on the first, we do kind of the cyclic operator on the first 5 bits and leave the last bit, qubit. OK, and that's the whole trick. And now it's going to be much more pleasant, as it turns out, to figure out the planes of rotation of this R. So that's what we'll do. We'll actually use this R all along instead of the original one. I know it's weird, but it'll make our lives easier. OK, so now every state that we'll ever encounter will look like, we could have a 0 here, but we could also have a 1 here, and similarly. So now we're actually in the example, we're in 12 dimensions rather than 6. Because the only states we'll ever encounter are ones that look like, in the A part, one of these 6 basic states from S, and the B part can span by 0 and 1.